Hello, welcome to TGM tutorials. In this tutorial we shall look at computing 2x2 determinants using elementary row operations. This is lesson 3. The properties of determinants of n 2x2 matrices. n 2x2 matrix can be stated in terms of elementary row or column operations, as we can observe in the following theorem. So we have the theorem: let A be a square matrix. Then, if B is the matrix that results from multiplying a row or column of A by a scalar C, then the determinant of B is equal to the scalar C multiplied by the determinant of A. If B is the matrix that results from interchanging two rows or two columns of A, then the determinant of B is equal to the negative determinant of A. If B is the matrix that results from adding a multiple of one row of A onto another row of A, or adding a multiple of one column of A onto another column of A, then the determinant of B is equal to the determinant of A. Here, remember that this theorem is just similar to the properties of determinants of 2x2 matrices. We are going to look at this example. Using elementary row operations to compute the determinant of the following matrix. We have a matrix A with entries 4, 12, negative 7 and 5. The determinant of this matrix will give us 1, 0, 4, just by multiplying elements in the major diagonal subtracted by the product of elements in the minor diagonal. Give us 1, 0, 4. Now, using elementary row operations, we are going to deduce this matrix into an echelon matrix. Echelon matrix are in this form. The forms given below, these forms are called echelon matrix. This one, the second one, is a reduced echelon matrix, and this one is just an echelon matrix. Okay, so we have 4, 12, negative 7, 5. From the examples of echelon matrices, we are going to make sure that where we have 4, we get a 1. So the operation that we are going to apply will be row 1 will be equal to 1 over 4 row 1, meaning we are multiplying every entry in the first row by 1 over 4. After carrying out that operation, we will get a matrix 1, 3, negative 7 and 5. Now, this matrix 1, 3, negative 7, 5 is the resultant matrix that we are getting after applying that operation by multiplying 1 over 3 to the first 1 over 4 to the first row. From the property given, this matrix, let's say this matrix is B. This matrix B, the determinant of this matrix should be equal to the determinant of A, the determinant of A multiplied by the scalar, the determinant of A multiplied by the scalar 1 over 4 according to the property. So that will give us determinant of B should be equal to 1 over 4 determinant A. B, the determinant, is given as 26, but for the determinant of A we have 104. So to make sure that the determinant of B is equal to the determinant of A, we are multiplying 1 over 4 by 104, which is giving us 26. Okay, we are going to apply another operation, this one, to make sure that where we have negative 7 here, we get a 0. And that will give us 1, 3, 0 and 26. 1, 3, 0 and 2, 6. From this one, we know that if the determinant of B is equal to, we are using the property which says that adding a multiple of one row or column of A onto another row or column of A, the determinant of B should be equal to the determinant of C. Let's say this is the determinant, this is B, and the resultant matrix that we have here is C. The determinant of B, 26, should be equal to the determinant of C, 26. We are going to carry out another operation to make sure that here where we have 26 we get a 1 by multiplying 1 over 26 throughout row 2. 1 over 26 multiplied by 0 we still get a 0, and 1 over 26 multiplied by 26 we get a 1. That is 1, 3, 0 and 1. Okay, this matrix, let's say this matrix is T. Here we have just applied the same property as we applied in the first operation here, and the determinant of D should be equal to 1 over 26 determinant of C. The determinant of D should be equal to 1 over 26 the determinant of C according to the first property. The determinant of D is equal to 1 and the determinant of C is 6. So to make sure that the determinant of D is equal to the determinant of C, we are multiplying 1 over 26, which is the scalar we used, by 26, and we are getting 1. Okay, let's look at this theorem. If A and B are n2 by 2 matrices, then the determinant of A, B is equal to the determinant of A multiplied by the determinant of B. We are going to look at the proof. If we let A be equal to that matrix and B be equal to that matrix, then the determinant of AB is equal to the determinant of the product of matrices of A and B. The determinant of AB should be equal to the determinant of product of matrices A and B, which is that multiplying the major diagonal subtracted by the minor diagonal will get that. Expanding this and simplifying it will get to this answer. Now I know that using these letters and symbols is more confusing, so let's try to use less complicated letters. If we let the elements of matrix A to be equal to the letters A, B, C and D, and the entries of matrix B to be equal to the letters G, F, H and J, then matrix A will be equal to that and B will be that. This will be A and this is B. The product of A and B is equal to this. Here the determinant of A is equal to AD minus BC. AD minus BC multiplied by the determinant of B is G J minus HF. So this part, the determinant of this part should give us this determinant, and this is equal to this. If we multiply the major diagonal and the minor diagonal, we are getting that. Expanding that, we are getting AGCF plus AGDJ plus BHCF plus BHDJ plus minus CGAF minus CGBJ minus DHAF minus DHBJ. Simplifying this one, we have like terms. For instance, negative CGAF plus this one AGCF. Doesn't matter the arrangement of the letters as long as we have common the same letters. AGCF